Welcome to this coding problem walkthrough. Today, we'll be tackling problem number 582, titled Kill Process. This problem is a fascinating challenge that involves simulating a tree structure and exploring parent-child relationships in a process hierarchy. It's a great test of your problem-solving and data structure skills. Let's dive in. In this problem, we are tasked with managing a hierarchy of processes, where each process is represented by a unique ID. The relationship between processes is described using two arrays, PID for the process IDs and PID for their parent process IDs. Each process can have exactly one parent, except for the root process, which has no parent and is represented by a PID value of 0. Additionally, a parent process can have multiple direct children. The goal is to terminate a specific process, identified by its kill ID, and as a result, also terminate all of its child processes, including their descendants recursively. The challenge is to return a list of all the processes that will be affected by this termination, in any order. The output of the problem is a list of integers, which includes the kill process ID and all other process IDs that will be terminated as a consequence. To understand how this works, let's go through an example. Suppose we have the PID array as 1, 3, 10, 5, and the PID array as 3, 0, 5, 3. Here, the kill ID is 5. The task requires us to determine which processes will be terminated when process 5 is killed. The output in this case is 5, 10, which we will explain next. To break down the example, the PID array 1, 3, 10, 5 corresponds to the processes, and their parent-child relationships are defined by the PID array 3, 0, 5, 3. This forms a tree structure where process 3, being associated with a PID value of 0, is the root. Process 3 has two children, processes 1 and 5. Additionally, process 5 has one child, process 10. If we terminate process 5, its child process 10 is also terminated. Therefore, the result is 5, 10, as these are the processes affected by the termination. Now consider another example. Here, the PID array is 1, 2, 3, 4, 5, and the PID array is 0, 1, 1, 2, 2. This creates a tree structure where process 1 is the root, with processes 2 and 3 as its children. Process 2 further has two children, processes 4 and 5. If we terminate process 1, the root, all processes in the tree, namely 1, 2, 3, 4, and 5, will be terminated. Thus, the output is 1, 2, 3, 4, 5, as every process is directly or indirectly affected by terminating the root. In yet another example, the PID array is 1, 2, 3, and the PID array is 0, 1, 1. This creates a simpler tree structure where process 1 is the root, and it has two children, processes 2 and 3. If we terminate process 3, there are no child processes under it. Therefore, only process 3 is terminated, and the output is 3. This demonstrates a case where the kill process has no dependencies, making the output straightforward. Finally, it's important to consider some constraints and edge cases. For example, if the kill ID corresponds to the root of a deep hierarchy, the output will include all processes in the hierarchy, as every process is directly or indirectly affected. Additionally, if the PID array contains only 0, it means there is a single root process, and killing it will terminate the entire system. On the other hand, if the kill ID has no child processes, the output will simply be a list containing that single process ID. These edge cases ensure the solution is robust and handles all possible scenarios effectively. To tackle the kill process problem, we start by analyzing its structure. Each process is represented as a node in a tree, with a parent-child relationship derived from the PID array. When a process is terminated, all its child processes, as well as their descendants, must also be terminated. This means we can think of the problem as traversing a directed graph, where the edges represent the parent-child links. The task is to traverse the graph starting from the process to be killed and gather all affected nodes. Since the input size can be quite large, with up to 10,000 processes, efficiency is crucial. We need an approach that allows us to traverse the tree quickly and avoid redundant computations. Initially, we might consider a brute force approach where we directly match parents to children by repeatedly scanning the PID array, but this can quickly become inefficient for larger inputs. The brute force approach relies on directly matching parent-child relationships by scanning the PID array repeatedly. To execute this, we begin with the process to be killed, then iterate through the PID array to find all processes that have the current process as their parent. For each of these children, we recursively repeat the procedure to find their descendants. Finally, we collect all processes that were terminated during this traversal. While this approach is straightforward, it has significant downsides. The main issue is inefficiency. Every recursive call requires scanning the entire PID array, leading to a time complexity of n squared, in the worst case. Additionally, the space complexity grows with the recursive stack, making it impractical for large inputs. Because of these inefficiencies, this method is not suitable for the problem at scale. A more efficient solution involves representing the process tree as a graph using an adjacency list. This representation allows us to avoid scanning the PID array multiple times. To implement this, we first pre-process the input to create a mapping where each process ID points to its list of children. Once the graph is built, we can use either breadth-first search, BFS, or depth-first search, DFS, to traverse it. Starting from the process to be killed, we visit all its children, then their children, and so on, collecting all reachable nodes. This approach is far more efficient, with a time complexity of n, since we perform only one pass to build the adjacency list and another to traverse the graph. The space complexity is also n, accounting for the adjacency list and the queue or stack used during traversal. This method eliminates redundant work and ensures the solution is scalable. Another potential solution involves using topological sorting, which leverages the fact that the process tree forms a directed acyclic graph, or DAG. To apply this method, we first build the graph and calculate the indegrees of all nodes. Then, we perform a topological sort to determine the order in which processes can be terminated. Finally, we traverse the graph starting from the target process and collect all affected nodes. While this approach is efficient, with a time complexity of n, it introduces unnecessary complexity for the problem at hand. Topological sorting provides a complete termination order for all processes, which is more information than we actually need since our goal is simply to traverse from a single starting node. Because of this over-engineering, the topological sorting approach is not the most practical choice for this specific task. The best strategy for solving this problem is the optimized graph-based approach using BFS or DFS. By pre-processing the input into an adjacency list, we eliminate the inefficiencies of repeated PID array scans, allowing us to traverse the process tree in linear time relative to the number of processes. BFS is particularly well suited for iterative implementations, while DFS is a good choice for recursive solutions. Both methods are equally efficient in this context. When comparing approaches, the brute force method is simple but too inefficient for large inputs, while topological sorting adds unnecessary complexity. The graph-based approach strikes the perfect balance between simplicity and performance. It ensures that we achieve the desired result efficiently while keeping the implementation straightforward, making it the most suitable choice for this problem. To solve the problem of killing processes in a tree structure, we first need to understand the input and the problem requirements. The input consists of two lists, PID, which represents the process IDs, and PID, which represents their parent-child relationships. For instance, if PID equals 1, 3, 10, 5, and PID equals 3, 0, 5, 3, PID I indicates the parent of PID I. The goal is to terminate a given process ID, referred to as kill, along with all its descendants in the hierarchy. To achieve this, we can leverage the fact that the parent-child relationships form a tree structure. This insight allows us to utilize traversal methods like depth-first search, DFS, or breadth-first search, BFS, to simulate the process termination. The first step is to parse the input and build a tree representation using an adjacency list. This can be efficiently implemented with a default dict in Python. The parent process IDs act as keys, and their corresponding child processes are stored as values in a list. This structure enables quick access to any process's children, laying the groundwork for the traversal phase. For example, given PID equals 1, 3, 10, 5, and PID equals 3, 0, 5, 3, the adjacency list representation of the tree would be process_tree equals 0, 3, 3, 1, 5, 5, 10. Here, process 0 is the root, with 3 as its child, and process 3 has children 1 and 5. Additionally, process 5 has a single child, 10. Once the tree is constructed, the next step is to perform a traversal to identify all processes that need to be terminated, starting from the given kill process ID. To achieve this, we can use either DFS or BFS. DFS involves recursively exploring all descendants of a node, while BFS uses a queue to explore nodes level by level. For the DFS approach, we define a recursive function that starts from the kill node, adds it to the result list, and then recursively visits all its children. This ensures that all processes in the subtree of the kill process are captured. The implementation begins by initializing the process underscore tree and a helper function for DFS. The DFS function continues by iterating over all children of the current node and recursively calling itself for each child. For example, if the kill process is 3, the DFS starts at 3, adds it to the result list, and then visits its children, 1, 5. From there, it explores 5's child, 10, visiting each node in depth first order. The final result list will contain all terminated processes. In this case, the output would be 3, 1, 5, 10. DFS is intuitive and effective for this problem, but it does rely on the recursion stack, which can lead to stack overflow errors for very deep trees. To avoid this, we can consider an iterative approach using BFS. BFS is particularly useful when recursion depth limits are a concern. Using a queue, BFS processes nodes in a level-by-level manner, ensuring that we capture all descendants of the kill node. The BFS implementation begins similarly by building the process underscore tree and initializing a queue with the kill node. In the BFS implementation, the queue is used to manage the nodes to be explored. Starting with the kill process in the queue, we repeatedly dequeue a process, add it to the result list, and enqueue all its children from the adjacency list. This continues until the queue is empty, ensuring that all processes in the subtree are visited. For example, if kill equals 3, the queue initially contains 3. We dequeue 3, add it to the result, and enqueue its children, 1, 5. Next, we process 1 and 5, adding them to the result, and eventually enqueue and process 5's child, 10. The final result is 3, 1, 5, 10, identical to the DFS approach. The adjacency list representation is efficient because it allows O1 access to the children of any node. Both DFS and BFS are viable traversal methods, with DFS being recursive and intuitive, and BFS offering an iterative alternative. Edge cases to consider include scenarios where the kill node is not in the PID list, in which case the output should be an empty list, or when the kill node is the root of the tree, leading to the termination of all processes. The result list is used to store all the processes that need to be terminated, and depending on the traversal method, either the recursion stack, for DFS, or a queue, for BFS, is used to manage nodes during the traversal. The time complexity of the algorithm is O(n), where n is the size of the PID list. This is because building the adjacency list takes O(n), and traversing the tree also requires visiting each node once, resulting in a total time complexity of O(n). The space complexity is also O(n), due to the storage requirements of the adjacency list in either the recursion stack or the BFS queue. In summary, this approach is efficient in both time and space, making it well suited for simulating the termination of processes in a hierarchical structure. By leveraging the adjacency list and carefully selecting the traversal method, we can handle large and complex trees effectively, while also accounting for edge cases to ensure robustness. This solution addresses the problem of terminating a specific process and all its descendants in a tree structure. Here's a step-by-step breakdown. 1. Tree construction. The PID list specifies the parent-child relationships between processes. We use a default dictive lists to map each parent process to its child processes. This forms a tree structure where each parent node points to its children. 2. Breadth first search, BFS. To terminate all processes starting from the given kill process, we use BFS. A queue, DEQ, is initialized with the kill process, and we traverse through its children and their descendants. Each visited node is appended to the to_kill list, which stores all process IDs to be terminated. 3. Output. Once BFS completes, the to_kill list contains all processes that need to be terminated, including the initial kill process and all its descendants. This list is returned as the result. Efficiency. The BFS traversal ensures we visit each process only once, making the time complexity O, n, where n is the total number of processes. The space complexity is O, n, as well, due to the storage requirements for the tree and the queue. This implementation handles edge cases, such as killing a process with no children, returns a list with only the kill process. A PID list with no parent-child relationships, e.g., all parents are 0. The code is concise, efficient, and adheres to the constraints of the problem. Here, we are implementing the solution to the kill process problem in Java. The first step involves constructing a tree-like structure to represent the parent-to-children relationships between processes. To do this, we use a hash map called process tree, where the key represents the parent process ID, and the value is a list of its child process IDs. We iterate through the PID and PID lists, and for each parent-child pair, we add the child to the corresponding list in the map. This effectively builds our tree structure. Next, we move on to the process of collecting all the processes that need to be terminated. To achieve this, we perform a breadth-first search, BFS. We initialize a queue with the process ID that needs to be killed and a list, to kill, to store the results. The BFS involves repeatedly polling the front of the queue, adding the current process to the to-kill list, and then enqueuing all its child processes if the current process has any children. This ensures that we traverse all descendants of the process being killed. Finally, once the BFS traversal is complete, the to-kill list contains all the process IDs that need to be terminated, including the parent process and its descendants. This list is then returned as the result, effectively solving the problem by identifying all processes that should be stopped in a cascading manner. This approach ensures that we efficiently handle the parent-child relationships and terminate all necessary processes in a systematic way. To solve this problem, we start by building the process tree. The PID list represents the IDs of processes, while PID represents their parent processes. Using the zip function, we pair each PID with its corresponding PID and create a mapping where each parent points to its children. For this example, the mapping results in a dictionary where process 3 has children 1 and 5, and process 5 has child 10. Additionally, process 0 acts as a root with child 3. This tree structure will allow us to traverse all descendants of the process we want to kill. Once the tree is ready, the next step is to initialize the traversal using breadth-first search, or BFS. We start the BFS with the process we want to kill, which is process 3 in this example. The queue is initialized with 3, and an empty list to _kill is prepared to keep track of all processes to terminate. In the first iteration of the BFS loop, we dequeue 3, add it to _kill, and enqueue its children, 1 and 5. In the second iteration, we dequeue 1, add it to _kill, but since 1 has no children, the queue remains unchanged except for process 5. In the third iteration, we process 5, adding it to _kill and enqueuing its child 10. Finally, in the fourth iteration, we dequeue 10, add it to _kill, and since it has no children, the queue becomes empty. At this point, the BFS traversal is complete. The result of the traversal is the list to _kill, which contains all processes that need to be terminated, 3, 1, 5, 10. This output represents the process we wanted to kill and all of its descendants in the tree. Now, let's look at another example with a simpler scenario. Here, we have only one process, 1, with a parent of 0. The process to kill is 1. First, we build the process tree, which is straightforward. Process 1 is the only child of 0. Next, we initialize the BFS with the queue containing 1 and an empty to _kill list. In the BFS loop for this case, we dequeue 1, add it to _kill, and check for children. Since 1 has no children, the queue becomes empty after this iteration. The final result is to _kill equals 1, which means only process 1 gets terminated. Now, consider an example with disconnected processes. Here, we have multiple processes, but not all of them are connected to each other. The input specifies processes 1, 2, 3, and 4, with 1 and 2 being children of 0, and 3 and 4 being children of 1. The process to kill is 1. To handle this, we first build the tree to map the relationships. The tree shows that 1 has children 3 and 4, while 2 is not connected to 1. We initialize the BFS with 1 in the queue and an empty to _kill list. In the first iteration, we dequeue 1, add it to to_kill, and enqueue its children 3 and 4. Next, we process 3, adding it to to_kill, and since it has no children, the queue remains with 4. Finally, we process 4, add it to to_kill, and the queue becomes empty. The result, to_kill equals 1, 3, 4, includes the process we wanted to kill and its connected descendants. This example highlights how the algorithm efficiently terminates all relevant processes using BFS, visiting each process only once, resulting in an O(n) time complexity. To analyze the time complexity of this solution, we start by looking at the process of building the parent-to-children mapping. The zip, PID, PID operation pairs corresponding elements from the PID and PID lists, and since there are n processes, this step takes O(n) time. Afterward, we iterate through these pairs to populate the process_tree dictionary. For each pair, we insert a child into the list of its parent, and since dictionary insertions and list appends are O(1) operations, the entire iteration also takes O(n). Next, we consider the BFS traversal, where we begin by enqueuing the kill process. In the worst case, if the kill process is the root of a tree containing all nodes, we would visit every single process. For each node dequeued, we process its children by appending them to the queue. Since each node is visited exactly once, and each edge in the tree is processed once, the traversal is proportional to the total number of nodes and edges. Given that a tree with n nodes has n1 edges, this step also takes O(n) time. Combining these, we see that both the mapping and traversal steps are linear in complexity. Adding the results from the previous steps, we find that step 1, building the parent-to-children mapping, takes O(n), and step 2, performing the BFS traversal, also takes O(n). Together, the total time complexity of the solution is O(n). Now, switching to space complexity, we begin with the process_tree dictionary. This structure stores the parent-to-children mapping, where each node holds a list of its children. Since the total number of edges in the tree is n1, the space required to store this mapping is proportional to O(n). Then, we have the BFS queue, which maintains the nodes to be processed. In the worst case, all nodes at the largest level of the tree might be stored in the queue. For a balanced binary tree, this maximum level contains about half the nodes, or O(n/2), which simplifies to O(n). Finally, we consider the to_kill list, where we store all the processes to be terminated. If all n processes are to be killed, this list would also require O(n) space. Adding these together, the total space complexity of the solution is still O(n). Summarizing the space requirements, the process_tree dictionary requires O(n) space, the BFS queue requires O(n) space in the worst case, and the to_kill list also requires O(n) space. Therefore, the total space complexity of this approach is O(n). Now, let's compare this optimized solution with a more naive approach. In a brute force method, we might repeatedly scan the PID list to find all children of the kill process. For every child found, we would recursively scan the list again to locate their children, and so on. This repeated scanning results in a time complexity of O(n², in the worst case, as each process could trigger a full scan of the list. The space complexity of the brute force approach, however, is minimal, typically O(1), since no auxiliary structures are used. In contrast, the optimized solution pre-computes the parent-to-children mapping and uses BFS, ensuring that each node and edge is processed exactly once. This reduces the time complexity from O(n² to O(n), while maintaining a space complexity of O(n), due to the use of auxiliary structures like process_tree, queue, and to_kill. In conclusion, the optimized solution is far more efficient than the brute force approach, achieving a time complexity of O(n) instead of O(n²). This improvement is made possible by pre-processing the input data into a dictionary that allows fast lookups, and by using BFS to traverse the tree structure systematically. While the space complexity is O(n), due to the use of the process_tree, queue, and to_kill list, this is a manageable trade-off with a significant reduction in time complexity. The solution demonstrates how leveraging auxiliary data structures and efficient traversal techniques can greatly enhance performance for hierarchical problems like this one. Common mistakes in solving this problem often arise during the initial setup or traversal of the process tree. First, constructing the tree incorrectly from the PID array is a frequent issue. To avoid this, ensure you're mapping parent-child relationships properly using a data structure like a hash map or adjacency list. This guarantees that every parent process points to its respective child processes. Next, edge cases can be easy to overlook, but they're critical. For example, consider scenarios where the PID array is empty, the process ID to kill doesn't exist, or the inputs are malformed or disconnected. These need to be accounted for to prevent runtime errors. Additionally, inefficient traversal is another pitfall. If you repeatedly look up parent-child relationships in an O(n) manner, you'll end up with poor performance on large datasets. Pre-computing the relationships in O(n) during pre-processing can save significant computation time. Lastly, there's the decision between DFS and BFS. While both are valid, DFS is often easier for recursive solutions. Choosing the wrong traversal method might lead to inefficiencies or incorrect results, so weigh the trade-offs carefully. Another potential challenge is handling cyclic dependencies. While these are unlikely in valid tree inputs, malformed inputs could introduce cycles, causing infinite loops during traversal. Designing solutions robust enough to handle such edge cases is essential. From an interview perspective, it's important to ask clarifying questions to confirm assumptions about the input. For instance, ensure the PID and PID arrays are valid and well-formed, and verify whether the kill process ID is guaranteed to exist in the input. Scalability is another key discussion point. Highlight how your solution can manage large datasets with millions of processes by leveraging pre-processing and efficient data structures like hash maps. Moreover, be prepared to explain your trade-offs, such as choosing DFS over BFS, and justify your decision with respect to space or time complexity. Finally, demonstrating a dry run with a small example can help validate your approach and showcase your problem-solving process to the interviewer. Now let's connect this problem to related challenges that can deepen your understanding. For example, in LeetCode 207, Course Schedule, you deal with topological sorting in a directed graph, which shares similarities in terms of graph traversal. LeetCode 310, Minimum Height Trees, involves optimizing tree traversal, while LeetCode 133, Clone Graph, focuses on graph traversal and cloning nodes. Lastly, LeetCode 102, Binary Tree Level Order Traversal, highlights BFS traversal in a tree structure. As for alternative approaches, you might consider using BFS instead of DFS. In this method, a queue is used to iteratively traverse child nodes. BFS can be advantageous in environments with limited recursion stack depth, offering a more iterative approach. The time and space complexity remain at O(n), but the choice between BFS and DFS often depends on the problem constraints and your implementation preferences. Another alternative is using the union find or disjoint set data structure. This approach groups processes by their parent and helps you retrieve all descendants of a kill process. While this method is powerful, it's less intuitive for this particular problem and may require additional bookkeeping to track all descendants. The time complexity is O(n) alpha n, where alpha n is the inverse Ackermann function, and the space complexity is O(n). Finally, an adjacency list with pre-processing can be a very effective strategy. By building a graph representation of the processes during pre-processing, you can traverse the data much more efficiently. Although pre-processing adds some initial overhead, it significantly speeds up traversal, making it ideal for large datasets. The overall complexity for this approach is O(n) for pre-processing and O(n) for traversal, with space complexity also at O(n). Each method has its own trade-offs, so select the one that aligns best with the problem's constraints and requirements. Great job on completing this problem. To summarize, we use tree traversal techniques like DFS or BFS to solve kill process efficiently. The problem reinforced the importance of understanding hierarchical data and using hash maps for optimization. Thanks for watching. Be sure to like, subscribe, and keep practicing. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!